Today we are kicking off our series on free body diagrams. And by the end of this series, you should master free body diagrams and be able to solve almost any problem on mechanics. However, today we are starting with the most fundamental scenario where a wooden block of mass m rests motionless on a flat horizontal tabletop. And by the end of today's video, we should be able to draw a complete free body diagram of the block by clearly labeling all the forces acting on the block with our defined coordinate system. Also, we should be able to apply Newton's second law to determine the magnitude and direction of the normal force exerted by the tabletop on the block. But before that, I would like you to pause the video, try your hands on this problem by drawing the free body diagram and also deriving the Newton's second law equation of motion for this block before proceeding to look at the solution. Let's dive in. So in this problem, we are given a block of wood that is resting on a flat surface. To draw the free body diagram, we need to first draw our coordinate system. And the coordinate system I'm going to use here is the Cartesian XY coordinate system. The vertical axis, which is our Y axis, we label it. And then the horizontal axis, which is our X axis, also well labeled. Next, we need to identify the directions. So if we place the origin here, then any force or vector that point upwards is going to be positive. And hence any vector that points downwards is going to be negative. Also, any vector that points to the right is going to be positive, and any vector or force that points to the left is going to be negative. So now we have clearly defined our coordinate system. With this block, we have to consider the center of mass of this block. And the center of mass is the point in this block where the total weight of this block is going to be acting. With that, we need to model this whole block as a point particle, such that we do not need to care about the internal structure of the table, and also we do not have to worry about the floor beneath this block. So with that, we have to draw our free body diagram such that we have the block as a point particle that is the center of mass of the block, and the block is our object of interest in this problem. So we have to use arrows to represent each force that acts on this block. And since the block is not accelerating, that is, it is not moving up or down, we need to know that the acceleration is 0. So the block is at rest, motionless, therefore the velocity is 0. Alright, so looking at this block, we know that it is interacting with the earth through gravitational pull. So we have the force of gravity that is acting on this block, and the direction for this force is vertically downwards. And we can represent that as Fg, and that is equal to the weight of the block. Another interaction on this block is from the surface of the table in support of the weight of the block. So that force acts perpendicular, that is at right angle to the two surfaces in contact, and it is pointing upwards because it is from the table upwards supporting the weight of the block. And this force is called the normal force, so Fn. In other notations, they use N. So vertically, these are the two interactions on the block. All right, so the block is one interacting with the earth through the gravitational pull on the block towards the center of the earth. And secondly, we do have the surface of the table supporting the weight of this block upwards. So that force is the normal force, Fn or N. But for the rest of this problem, I'm going to stick to Fn. Horizontally, we are not given any forces acting on this block. Back to our free body diagram, we have the downward force, which is the force of gravity. And since it is a vector, it starts from the center of mass. And then at a certain length, we have the tip of the arrow indicating the direction, and we write that as Fg, and that is equal to the weight of the block. Also, vertically upward, as we've already established, there is the force of support on the weight of this block, and that is vertically upwards. But the golden rule is that since this block is not accelerating up or down, it means that the force of gravity is equal to that normal force. So if we are to draw this to scale, both length of these vectors have to be equal. So in blue, we have the normal force pointing upwards, and it should be equal in length to this force of gravity acting vertically downwards. So we have the normal force Fn. So vertically, these are the two forces that are interacting with this block. Horizontally, we do not have any information about any forces for now because this is just the fundamental scenario we are starting with. So these are the forces we have acting on this block, resting on a flat surface. Next, let's look at the Newton's second law to derive the equations of motion on this block. So Newton's second law says the net force, so the sum of all the forces acting on this block in any direction, has to be equal to the mass of the block times the net acceleration produced by the force. So since we have established a coordinate system, we have to do this Newton's second law for the vertical and the horizontal component of the forces. Okay, so for the horizontal component, the net force acting along the x direction is equal to the mass times ax. So the net force along the horizontal direction is equal to the mass of the block times the horizontal net acceleration. But we don't have this block moving left or right, meaning it is not accelerating in the horizontal direction. So that tells us that ax is equal to 0. All right. So the net force along the x direction is equal to 0. And that is all we can write for this part of the motion. Now let's look at the y component. So for the y component also, we should have the net force along the y direction is equal to the mass of the object times the acceleration of the object along the y direction. So now, since we've established this, we know that there are two forces acting vertically along the y direction. With the help of our coordinate system, we can specify the upward force, which is Fn, which is positive, and then plus, because we are summing all the forces acting on this block, so plus Fg, that's the force of gravity, but it is pointing downwards. And since we are doing a vector addition of these two forces, we need to consider the direction. So minus Fg, and then that should be equal to the mass times the acceleration in the vertical direction. Again, in the vertical direction, since this block is not moving up or down, then that vertical acceleration ay is 0. So that means that the right hand side of this equation goes to 0 because the mass of the block times 0 acceleration is equal to 0. So we can further simplify this. So the normal force plus minus multiplying, so that gives us minus, and then Fg, and that is equal to 0. So clearly, if we add Fg to both sides, so plus Fg here is equal to plus Fg here. All right, so we did add Fg on both sides, so we can clearly see that minus Fg plus Fg is just 0, and then here we have 0 plus Fg, so that gives us Fg. All right, so now we are left with the normal force Fn is equal to the force of gravity. And that force of gravity is equal to the weight of the block, and that is equal to the mass of the block times acceleration due to gravity. And here we clearly see that for an object that is resting on a flat surface, the normal force is nothing but the weight of the object due to gravitational pull. And the normal force is in the opposite direction because it is the force supporting whatever force gravity is pulling the object downwards with. So this is how to write a free body diagram for this fundamental scenario, and this is going to be a series of problems on how to draw free body diagrams for different scenarios. Thank you for watching up to this point, and if you are new to this channel, don't forget to like and share and also subscribe to support the channel. And if you are already a member of this channel, thank you so much, and until then, I'll see you in the next video. Bye bye.